What if the most convincing thing in the room was never actually there? Holography wasn't born in Silicon Valley. It came out of a London laboratory in the late 1940s, when physicist Dennis Gabor figured out how to encode three-dimensional information onto a flat surface, using light itself as the recording medium. Here's the misconception that trips almost everyone up. Holograms aren't two-dimensional images dressed up to look fancy. They encode genuine depth, light from every angle, not just one frozen viewpoint like a photograph. A hologram is a recording of light patterns. When those patterns are reconstructed correctly, your eye receives the exact same light signals it would receive from the original object sitting right in front of you. Creating a hologram requires two laser beams working in tandem. The first, the reference wave, travels directly to the recording medium. The second, the object wave, bounces off the subject first, carrying its three-dimensional shape encoded in its ripples. When those two waves collide on the recording surface, they create an interference pattern, an intricate fingerprint of light and dark fringes that stores the object's full three-dimensional geometry, invisible to the naked eye, until light reconstructs it. Reconstruction is the magic act. Shine a laser through that recorded interference pattern, and the light bends precisely, rebuilding the original wavefront. Your brain reads that wavefront as a solid object floating in space.
Here's the fact that genuinely surprises people. Holograms are extraordinarily difficult to replicate.
The interference pattern is so complex that counterfeiting it without the original laser setup is practically impossible, which is exactly why holograms guard your credit cards. For decades, holography lived in science fiction, then it crossed over. In 1983, American banknote holographics produced the first mass-market security holograms for Visa credit cards, the moment holography stopped being a laboratory curiosity and became a global commercial product embedded in hundreds of millions of wallets. Consider what the BBC actually tried, placing an acrylic pyramid on top of a flat-screen television. Light from the screen bounced off the pyramid's angled faces, creating the illusion of a floating three-dimensional image visible from multiple sides at once. The pyramid works because each of its four angled faces reflects a slightly different perspective of the same image. Your visual system stitches those perspectives together and concludes, confidently, incorrectly, that a solid object is hovering in front of you. But here's where it gets harder. The BBC pyramid isn't true optical holography. It's a clever illusion built on reflection geometry. Real holography encodes wavefronts physically onto a medium, a fundamentally different and far more demanding process. Ordinary light from a bulb is chaotic, waves traveling in every direction, out of phase with each other. Laser light is coherent. Every wave crest lines up. Without that coherence, the interference pattern that defines a hologram can't form. Drop two stones simultaneously into still water. Where their ripple rings overlap, you get a fixed pattern of peaks and troughs. Holography does the same with light waves, freezing that collision pattern permanently onto a light-sensitive surface. In medicine, three-dimensional accuracy is the difference between a clean incision and a catastrophic one. Holographic technology now generates detailed, navigable representations of organs, giving surgeons a spatial read of anatomy that flat scans can't deliver. Holograms fool the eye so effectively because of how vision actually works. Your brain doesn't see the world directly. It constructs a model from light signals. Feed it the right signals, and it builds the wrong, completely convincing model. Your two eyes sit roughly 5 centimeters apart. Each sees the world from a slightly different angle. Your brain compares those two images and extracts depth from the difference. A hologram delivers two genuinely different perspectives, one per eye, exactly as reality does. Holographic technology is also reshaping classrooms. Students can interact with holographic reconstructions of historical artifacts and scientific structures, rotating a Roman gladius or walking around a DNA double helix without ever touching the real object. Here's the twist most people never register. Holographic technology has been quietly protecting documents and identities for years. The shimmering patch on a passport or banknote is a mass-produced hologram whose complexity makes it one of the most reliable anti-fraud tools ever deployed. Replicating a security hologram requires the original laser setup, the original interference geometry, and the original recording medium. Remove any one of those three, and the copy fails. That's not a loophole. That's the physics working exactly as intended.
Artists discovered holography almost as soon as scientists did. British artist Margaret Benyon exhibited holographic works at the Nottingham University Art Gallery in 1969. Among the first gallery shows anywhere to treat holography as a fine art medium. Her pieces shifted and revealed hidden layers depending on the angle from which you viewed them, making the viewer an active participant rather than a passive observer. The next frontier is mixed reality, overlaying holographic images directly onto the physical world so that digital objects occupy real space, respond to real lighting, and interact with real surfaces. Microsoft's HoloLens 2, released in 2019, already does this. Surgeons at Case Western Reserve University use it to overlay holographic anatomy onto cadavers during medical training, collapsing the distance between the recorded and the real in a working classroom. But here's the question sitting underneath all of this. If a hologram delivers every visual signal your brain uses to confirm something is real, at what point does the distinction between the recorded and the actual stop mattering to the person experiencing it? In medicine, the distinction matters enormously. A holographic organ model is a planning tool, not a replacement for real tissue. The value is in the information it delivers, not in mistaking the model for the patient. That's a line practitioners are careful never to blur. Here's the payoff. Holography works not because it creates something new, but because it speaks the brain's native language fluently. Light carries information. The brain reads that information. A hologram writes the message in the correct format. Optical holography teaches a deeper lesson about information. Every point on a holographic plate contains data about the entire image, not just its local region. Damage part of the plate and the full image survives at lower resolution. The redundancy is built into the physics. That distributed redundancy is now inspiring real data storage research. Microsoft's Project HSD, holographic storage device, investigated encoding data using holographic storage techniques so that no single damaged region could destroy the complete record. The same principle that keeps a scratched hologram intact is being engineered into fault-tolerant storage architectures designed to outlast any single point of failure. Remember the opening question. What if the most convincing thing in the room was never actually there? Holography answers it precisely. The object is absent, the light information is present, and to a brain evolves to trust light. That's enough. Consumer electronics are the next delivery vehicle. Looking Glass Factory, a Brooklyn-based company, already sells holographic displays that project depth without glasses or headsets. Their Looking Glass 16 model targets developers building spatial interfaces for medicine, design, and entertainment. The hardware exists. The question now is how fast the content ecosystem catches up. The remaining hard problem is full-color, full-motion holography at consumer scale. Recording and reconstructing moving three-dimensional scenes in real time demands computational power and optical precision that current hardware is only beginning to approach. Here's the moment that made millions of people suddenly pay attention. At Coachella 2012, a holographic projection of Tupac Shakur, dead since 1996, appeared on stage alongside live performers in front of a crowd of thousands. The technology was a Pepper's Ghost variant built by Digital Domain and AV Concepts. Not true optical holography, but the public reaction proved something concrete.
When the illusion is convincing enough, the audience stops asking how it works and starts asking what else is possible. Dennis Gabor encoded three-dimensional reality onto flat film in a London lab in the 1940s. 8 decades later, that same principle is guarding your passport, training your surgeons, and quietly rewriting what presence means. The illusion was always the most honest thing in the room.